Hi, in this video, we want to take a look at hypothesis testing. Okay, so what we're going to do here in this video, we're going to start with like an initial framework of just looking at making a decision using hypothesis testing. And I'm going to justify why is it that we reach conclusions with this weird approach. All right, so what we want to do, we want to have a less subjective decision-making process while we consider the situation at hand. So we consider the risk of making a mistake in terms of likelihood, the risk of making a mistake in terms of the ramifications, and we want to incorporate data and statistics into this process to get a full control over the situation. All right, so we're going to be focusing a lot on the mistakes that can happen when we reach a conclusion. All right, so the first thing that we need to keep in our minds as we approach hypothesis testing is if we are using data, then we don't know what's going on. Because if we knew what was going on, we wouldn't bother with data. Okay, so always keep that in your mind. Anytime that we are using data, we don't know what's going on. Otherwise, we wouldn't bother with the data in the first place. Okay, so next thing I want to say about hypothesis testing. All right, I'm going to give an example. This is from the Royal Statistical Society. There were several conferences, science conferences, and the Royal Statistical Society went and interviewed and asked questions of scientists about hypothesis testing. Now, these were professional scientists that use hypothesis testing professionally. And the article I read, from the Royal Statistical Society, concluded that not one of those scientists got hypothesis testing correct when they explained it. Okay, so let's think about that. This means that people who professionally use hypothesis testing frequently do not understand it correctly. Okay, so that means that if you don't understand hypothesis testing, if you are confused by it, you're normal. Furthermore, if you screw up something with hypothesis testing and you're using it and you're working through it, you know what that means? You're normal. Okay, so if you feel like you're getting beat up by this topic, which a lot of students do, you feel like you're overwhelmed, you feel like this is tough, it's okay. This is a very different way of looking at making a decision. It's a good solid framework. That's why it comes up so often. At this point, it's taught in high schools. Now, this is like we're trying to teach it in high schools so that we get a full understanding of it so that we can address these problems early on. This is used especially in terms of like pharmaceuticals and medical research heavily. And the scientific researchers use this a lot. Okay, so our goal is to reach a conclusion, and we want to use data and mathematics to fully understand our decision-making process. All right, so in this video, we're not even going to make a decision. We're going to talk about making a decision, and we're going to analyze making a decision so that we can have a solid framework going forward. All right, so the next thing I want you to keep in your mind as we work through this, with hypothesis testing, our goal is just reach a conclusion. All right, well, we want to do more than just reach a conclusion. We want to consider the risk in terms of the probability of a mistake, so the risk of a mistake in terms of the likelihood of screwing up, and we want to consider the risk of a mistake in terms of the repercussions of making a mistake. All right, so we're going to use data and theoretical statistics to fully understand the situation that we are wading into. All right, so to start out, we're only going to consider two possible conclusions. All right, so this is as simple of a conclusion as possible, that we're just going to say it's one or the other. We're going to have one of two choices, and we're going to conclude that one is correct. We're going to conclude that the other is not. Potentially, we can use hypothesis testing anytime we can gather data and estimate a probability distribution. so we're going to be using data and probability distributions. It's most natural for us to start out with making conclusions in terms of mathematical statements. And so that's where we're going to start. And so it seems very weird to be talking about like population averages or population proportions or you know, the amount of a variance or the ratio of variances in different you know, situations in hypothesis testing when you're taking your introductory statistics course. But if we look at this framework, it's the most natural first step for this. So this is why we're going through, you know, things like inequalities in terms of making a decision, because there's two possibilities and it's very mathematical. It lends itself very naturally to this framework of conclusions. Okay, so now I want to talk about the naive approach to reaching a conclusion using data. Or well, actually, I'll back up. The first thing I could do to reach a conclusion is I could just use subject matter knowledge, and I could say, you know, I could reach a conclusion without even looking at data. That's definitely a reasonable thing to do, and that's what we do the vast majority of our lives. So, you know, we just, you know, we're moving through life so quickly. We're doing stuff. We need to reach a decision, and we just use our experience and our knowledge of what's going on, and we just reach a conclusion. Okay, well, that's not very statistical, so I'm not going to really talk about that because there's no framework to analyze that. So let's go ahead and go very shallow into the data and statistics world. I'm going to call this naive hypothesis testing. All right, so in naive hypothesis testing, what we're going to do, we're going to reach a conclusion without considering making a mistake. Like we're going to look at the evidence that we have very briefly, and we're going to reach a conclusion and we're going to move on. Okay, so we're not going to go that deep into the situation, and we're not going to analyze anything in terms of risk. All right, so let's say that we want to know if the population average of a random variable is positive or negative. So two possibilities, positive or negative. Ignore the possibility of zero just for the moment. We'll get to that later in the video. All right, so we've got two possibilities. Either the average is greater than zero or the average is less than zero. All right, one of two choices. All right, well, what I could do, I could go out, I could collect some data. I take my sample average. If my sample average is positive, I conclude that the population average is positive. If the sample average is negative, I conclude that the population average is negative. All right, that's a very reasonable way to approach. Now, there's some shortcomings of this. There's some aspects that initially you wouldn't think about, even though this is a very data-driven way to reach a conclusion. First and foremost, it does not consider the repercussions of an incorrect conclusion. All right, so if I make a mistake, let's say that in reality, the population average is negative, but my data gave me a positive sample average, then I reached the wrong conclusion. I have to deal with the consequences of being wrong. If the sample average is positive, but my data gave me a negative sample average, then I made a mistake. I made an error. I have to deal with the consequences. All right, so first and foremost, this framework does not address the repercussions of making a mistake, of reaching the incorrect conclusion. Now, it also doesn't consider the likelihood of an incorrect conclusion. All right, so there's two things going on when we talk about the risk. There's the magnitude of like the penalty for being wrong, and there's a likelihood of us making the wrong conclusion. We have to include both if we want a full, complete situation. All right, now the next thing that is a shortcoming is that if I have normally distributed data, I didn't take any use of that. I didn't take advantage of that knowledge. I didn't pull that in. So if I have knowledge that I didn't take advantage of, then I'm not making the most completely informed decision possible. So I want to pull in knowledge about the probability distribution to get a more complete point of view. So there are three shortcomings of the naive hypothesis testing approach. Okay, so We want to focus on risk at this point. So risk, I've got the likelihood of making a mistake, and I've got the magnitude of the penalty for making a mistake. Now remember, when we talk about making a mistake, we are always in the situation where we don't truly know what's going on, so we're using data to fill in that unknown knowledge. And so when I reach a conclusion, no matter what I do, I am taking this risk of reaching the wrong conclusion. So let's consider the possible mistakes when reaching a conclusion. Okay, so there's two possible real world, what's actually going on situations. Either the population average is positive or the population average is negative. All right, this part of the table is what is the true correct result. One of these two is correct. Now, what could happen is that we could conclude that the population is positive, average, or we conclude that the population average is negative. Okay, so there's two possible true aspects. We don't know which one's correct, and there's two possible conclusions. So we have four possibilities. All right, so if the population average is positive and we conclude that's positive, then we made the right call. Good job. If the population average is negative and we conclude that the population average is negative, we made the right call. Good job. Now, here is where the risk starts coming in. The population average, it could be positive, but we could conclude that's negative. That means that we made a mistake. There's going to be problems. If the correct conclusion is that the population average is negative, but we conclude that it's positive, we've made a mistake. All right, so one of these four are going to happen. And of course, we want the correct conclusion, but we also want to make sure that if one of these mistakes has a very severe penalty, very severe repercussions, we want to avoid that just to make ourselves safer away from the worst result. Okay, so let's think about a situation involving like pharmaceuticals. Let's say that one possibility is that the medicine has life-threatening side effects. The other possibility is that the medicine does not have life-threatening side effects. All right, very, very different conclusions, right? One of two choices. If I'm holding a medicine in my hand, either it has life-threatening side effects or it does not. Okay, so what are the outcomes from an incorrect conclusion? All right, so now we're actually articulating the risk. If the medication has life-threatening side effects, but we conclude otherwise, so we conclude that it's safe, but it's not, patients will die. All right, that's a pretty severe penalty, repercussion. That's a problem. Let's think about the alternative error. Let's say that the medicine does not have life-threatening side effects, but we conclude otherwise. So here, the medication does not have life-threatening side effects, but we conclude that it does. We made a mistake. Well, what's going to happen? Well, patients will receive a different treatment. So they're not going to be left high and dry. They're just going to be treated in a different manner. Now, our company isn't going to make as much money because now the medication is not going to be used, but compared to getting sued for killing patients with medications, that's not too bad. All right, so we can see that patients just receiving a different treatment is a much lower penalty for making a mistake. Oh, okay, so now I want to think about both of those. Because when I reach my conclusion, I want to make sure that I don't conclude that there's no side effects unless I'm really, really sure of it. So I need strong evidence to conclude that there's no side effects for me to actually reach that conclusion because of the severity of the outcome of a mistake. The ramification of these mistakes is absolutely lopsided. And so we have a huge imbalance on this. So we're not going to conclude no lethal side effects unless we have strong evidence that that is the correct conclusion. Okay, so we have two possible mistakes. I want to avoid both of them, right? I want, honestly, we truly want to just have the right piece of information without data, and I just want to proceed. But remember, we're talking about the situation where we don't actually know what's going on. That's why we're using data. Okay, so I have to take a risk in some way. No matter what I do, there's going to be a risk that I made the wrong choice. Okay, well, it's a quirk of mathematics that in most situations, that we cannot control the risk of both types of mistakes. So what we do, we control the risk of the more severe mistake. So what I'm going to do is I will control the risk of concluding that it's safe when it's not. And I'm going to, to a large extent, I'm going to ignore the risk of the other one. All right, so, just for our population average example, let's go ahead and just say that concluding that the sample average is negative when the sample average is positive, let's say that is the more severe mistake, that I have a bigger penalty, like, worse things happen under that mistake. And let's say that if we were to conclude positive, when in reality it's negative, it's a mistake, it's a problem, but it's not as severe. Okay, so let's go ahead and just change our table a little bit so that we have like a severe error here and a mild error here. So I want to avoid this mistake pretty bad. So that's going to be, something that's going to be very important to us. All right, so mathematically, we can only control the risk of one of these two errors in most situations. So to control that risk, we're going to use the possible correct conclusion in terms of a probability distribution with the worst error outcome to determine the probability distribution. Okay. All right, so we call this possibility the null hypothesis. All right, so our null hypothesis is going to be the one where we avoid the more severe mistake. All right, so we're going to set up a framework so that we are prone to going with a conclusion that cannot, create a problem. So you'll notice that here, to have the more severe mistake, I have to conclude that the population average is negative. Okay, so if I make it so that in my framework, my conclusion reaching framework, my process of reasoning, if I make it so that I'm prone to concluding that the population average is positive, then I am prone to not make this mistake. Okay. All right, so what this means is that if we do not have strong evidence, we are going to go with the conclusion that cannot give us the severe error. All right, so I only go away from that when I have strong evidence. Okay, so unless I have strong contradictory evidence, I'm going to go with the null hypothesis. Okay, so now something about this. Because the null hypothesis is so important, we're going to use that one to be the one that determines our probability distribution as we're working through this. So in the mathematical control of risk, the equal sign goes with the null hypothesis. This is very important. Now we're going to call the other hypothesis the alternative hypothesis. So the null hypothesis is the one that we are prone to going with right out of the gate. The alternative hypothesis is the one that we will go with if we get strong evidence that it is correct. Okay, so I've got two possible conclusions, and then I look at which ones can generate a more, like which mistake is more severe. Okay, so what I'm going to do is I'm going to set it up so that the null hypothesis is the one that if I make if going with the null hypothesis is wrong, I get a lower penalty. The alternative hypothesis is where if I go with it and it's wrong, I have the more severe penalty. Okay, so null hypothesis, if I conclude the null hypothesis correct, then either I'm correct or I suffer mild consequences. If I conclude the alternative, hypothesis correct, then either I made the right choice or I'm dealing with a more severe penalty. All right, so let's go ahead and write out our hypotheses in terms of our population averages. So H sub 0, H sub O is the null hypothesis, and H sub A is the alternative hypothesis. And remember, equal signs always go with the null hypothesis because the null hypothesis is the one that determines our probability distribution. All right, so now let's go ahead and incorporate this vocabulary into our table. So now, one possibility is that the correct conclusion is that the null hypothesis is correct. One possibility is that the alternative hypothesis is correct. We can conclude that the null hypothesis is correct, or we can conclude that the alternative hypothesis is correct. And then things remain the same on the table. Okay, well, hypothesis testing is so common, so frequent, that these two types of errors have special names. And these special names are kind of confusing. It's just vocabulary. And if you're wading into this concept, you have to just basically memorize this. Okay, a type 1 error. A type 1 error is that the null is correct, but we make a mistake and we go with the alternative. So remember, if it's an error, it's a mistake. Type 1 error is that the null is correct. How do I remember this? Which one do I write first? You notice that I wrote the null first. Type 1 error is the first one is correct, but I make a mistake. Type 2 error, the alternative is correct, but we go and make a mistake. So type 2, the second one is correct. So if you remember, when we write our hypothesis testing, we always say the null, then the alternative. The null is our baseline, our benchmark, the one that we are prone to going with. So it is the first one that we state. The alternative is exactly that, the alternative hypothesis. So we say it's second. So type 1 error, the null is correct, but we made a mistake, we made an error. Type 2 error, the alternative is correct, but we made an error. Okay, so let's go ahead and incorporate this vocabulary onto our table. So the correct conclusion is the null, or the correct conclusion is the alternative. We can either conclude that the null is correct, or we can conclude that the alternative is correct. If the null is correct and we made a mistake, then I'm in this situation, that's a type 1 error. Null goes with type 1 error. If the alternative is correct, but we made a mistake, that's a type 2 error. Okay. So now we've been able to articulate what are the risks that's happening? What are the possible mistakes that could occur? And we formulated which one is more severe than the other, and that's led to us, having a formal structure on how we write down our hypotheses. Okay, so the next question is, how much risk are we willing to take? Okay, if you're not willing to take any risk at all, you have to just get out of the game. We wouldn't be doing this if you weren't willing to take some kind of risk. So you know that it's a positive number, so pick something. Okay, so what we're going to do, we're going to basically come up with a probability of a mistake. And if it's, that will be my risk tolerance of a mistake. So this will be my type 1 error risk tolerance will be stated in terms of a probability. Now, if it was 0.5, that means that I am just, 50-50. I don't really care that much about making a mistake. So alpha is going to be small. It's going to be on the smaller side. Typically, alpha is equal to 0.05. That's the most common value. Other common values are 0.1, 0.05, 0.01, 0.001. These are all common type 1 error risk tolerance. Okay, now remember, in mathematics, we can only control one type of error risk. And therefore, we're going to control the type 1 error risk because that's the one with the more severe penalty. Okay, so alpha is our type 1 error risk tolerance. And so this is the worst mistake error. Beta is our type 2 error risk tolerance. In most situations, we can only address one of these errors mathematically. And so we only address type 1 errors at all. So what we're going to do, we're going to establish what alpha is, and we're pretty much going to ignore beta. In more advanced hypothesis testing situations, we will consider both. Okay, so now let's incorporate known aspects of the probability distribution. So we need to reach a conclusion about the mean of a normal random variable with variance sigma squared. All right, so I need to make a decision. Either I conclude that the true population average is positive or 0, or I conclude that the population average is negative. Remember that I've got an equal sign here because nulls always get the equal sign. All right, so I'm going to go with the null hypothesis unless I have strong contradictory evidence. Okay, well, let's think about strong evidence. What would strong evidence be? Well, I'm going to go out, I'm going to collect some data, I'm going to look at my sample average. I'm going to use my sample average to get insight into the population average. So let's say that I collect my data and my sample average is 10 million, positive 10 million. I mean, that's pretty strong evidence that the population average is positive, right? Okay, so this is strong evidence that the null is correct. Now, let's think about another scenario. Let's say I was to go out, collect my data, and I get a sample average of negative 10 million. Well, I mean, that's pretty strong evidence that the population average is negative. Okay, well, so it's easy to reach a conclusion why I have strong evidence. Here, we want to figure out what do we do when it's in the gray? When is it that we don't have strong evidence? All right, so if our data is not extreme, how do we make a judgment call? Where is the cutoff where I say null is on this side and alternative is on this side? So we need a cutoff where I make it, so if I have something more extreme than this cutoff, I go with the alternative. If I do not have something more extreme than this cutoff, I go with the null. Okay, so what I need to do, I need to find a cutoff value. So what we want to find a cutoff value so that the probability that our sample average is less than that cutoff is equal to our risk tolerance. Okay, so here is our risk tolerance. This is how much of a risk we are willing to take. Okay, so from a probability point of view, I'm basically saying that if things were completely random, I would I would take a risk of the wrong mistake in terms of a type 1 error, no more than this frequency in terms of probability. All right, well, I'm going to be using my sample average. And if I get something more extreme than my cutoff, I'm going to go away from the null hypothesis. Remember, if I don't have extreme evidence, I go with the null hypothesis. So if I see something extreme, I go away from the null in favor of the alternative. And how extreme is extreme? We're using our risk tolerance to establish that cutoff. Okay, so what I'm going to do, I see that I'm using a sample average, right? And we're using a normal random variable. Okay, well, if I have a normal random variable, then automatically if it's independent, identically distributed, then my sample average is a normal random variable, but with reduced variance and with the same mu. All right, so what we're going to do, I'm going to take the normal distribution with population average of 0. The variance is going to be sigma squared divided by the number of observations in my data. Now I have a probability distribution. I'm going to use quantiles to figure out what is that cutoff right here. And so then I have a cutoff value for deciding when is it extreme enough for me to go away from the null in favor of the alternative hypothesis. All right, so now let's talk about reaching that actual conclusion. All right, so this part is weird, and we're not going to say it in plain English. Why is it that statisticians use such funny wording on this? All right, what we're going to say, we're either going to say we fail to reject the null hypothesis, or we're going to say we reject the null hypothesis in favor of the alternative. Those are two very funny worded sentences. Why do we do this? Okay, well, think about the framework that I just built up. I set it up so that really by default, I am prone to going with the null hypothesis. Or I am prone to go with the null hypothesis. Okay, I'm really prone. Like if I go 0.05 for alpha, that means that overall, like naively, I'm approaching, going with the null with a 95% chance. All right, a 95% chance of something and then it occurs, that's not surprising. Okay, so it's so lopsided, so extreme, I'm so likely to go with the null hypothesis that it really is not that big of a deal. And so what we say, we don't say we go with the null hypothesis, we say we fail to reject it. So basically I'm saying we did not see extreme contradictory evidence when I say we fail to reject the null hypothesis. Now, if I go with the alternative hypothesis, I do not say that in plain English. I say we reject the null hypothesis in favor of the alternative. All right, now, another reason why we use this funny wording is remember that we're using data. We don't actually know the true outcome. There is a chance that I have a bad sampling process. There's a chance that the person recording the data made a mistake. There's a chance that my measurement instruments were broken. There's a chance that some of my data was omitted. There could be problems. So what I'm basically doing, I'm trying to cover my own backside and say that I don't say one or the other is correct. I say, you know what? We reject it in favor of the alternative because we have sufficient evidence to say that. Or I'm going to say we fail to reject the null hypothesis because I still don't actually know. But in literature, we say I fail to reject the null hypothesis if we're going to go with the null as being our conclusion, or we say we reject the null hypothesis in favor of the alternative if we're going to go with the alternative. All right, so now what are the steps in hypothesis testing? First and foremost, I'm going to establish what are my hypotheses, my null hypothesis, my alternative hypothesis. Remember, the equal sign goes with the null. Next, I'm going to determine my risk tolerance. In the vast majority of cases, I address the risk tolerance of a type 1 error, the risk of a more severe mistake, and I don't address the type 2 error. I don't worry about beta. Then I'm going to determine the probability distribution that I will use for hypothesis testing. I'm going to determine the cutoff or cutoffs for the different conclusions. I'm going to gather my data and compare my results to the cutoffs. So something that I want you to notice is all of these steps occur before I even touch data, before I collect data, before anything happens with data. And then I state my conclusions in terms of we fail to reject the null hypothesis, or we reject the null hypothesis in favor of the alternative. All right, this is a lot to unpack. Please go through and try to, look at this again, watch the video a couple of times, make sure you get a feel for why is it that we're doing this. Number one, if I knew what was going on, I wouldn't be using data. I need to reach a conclusion using data. Okay, I want to incorporate the risk of a mistake. All right, and when I say risk, I mean the likelihood of a mistake and the penalty for making a mistake. I want to incorporate that into my system, and I want to have a system that is less subjective. Okay, and so this is why we use hypothesis testing. All right, so risk avoidance of a type 1 error really is the driving fact for hypothesis testing. Well, that's all I've got for you. Take care and goodbye.